Good morning, Paul.
Hello. Good afternoon, Tomer. How are you?
Fine, thank you.
So I'd like to welcome everybody to join us. I'm Paul Briscoe with Tag Video Systems, and joining me today is Tomer Schechter, our Chief Technology Officer. Officially, hello, Tomer.
Hi.
We're going to talk today about latency, particularly in live production. Latency is a hot topic these days, especially as we move to IP infrastructures. Latency is an interesting topic. Latency is a new thing. If we look at television broadcasting and we go back to the earliest days, the TV camera, the picture was scanned out by a little beam going across the front of the image sensor. And the time from that beam scanning that camera to the time it lit up the display in the viewer's home was measured in tens of microseconds. It was literally propagation delay through simple electronic devices, the propagation delay across the transmission path, and so on. And so latency never really was a thing, especially in the analog era. But when we arrived in the digital era, we started doing things using technologies that required processing time. And these things escalated on us. Things such as putting a DVE in the vision mixer. You immediately incur a frame of delay going through your DVE. And things like this. So as we've added technologies and as we've advanced technologies, we found that latency has become more and more of an issue. As we move to IP and pure COTS-based IP, the challenge grows even more because we're using protocols now with SMPTE 2110 that have buffer times on which require latency accommodation. If we put a number of the devices in a serial path, these latencies add up serially and so on. So really, the interesting question is what is important when it comes to latency, and where does latency come into the system, and what can we do about it? The reality here is we can't really do much about it. It's a technological thing. If we want to go back to analog video, we can remove latency, but we're not going to be doing that. So all of the system components between the glass in the camera and the glass or plastic on the front of the viewer's set contribute to this latency. And we're not going to talk too much about distribution latency today. That's the biggest piece of latency in systems. But we will talk about the production systems a little bit. And latency is important not just from a perceptual and operational point of view, but there are things to consider such as maintaining lip sync. So we'll chat about that. And then the other thing we'd like to touch on is what happens when we move to the cloud. It's all great when this stuff is hardware and software in your own equipment racks. But when you move that up to the cloud, and now you have to get up to the cloud with your content, you have to produce in the cloud, you have to interact with a cloud production system from a live human distributed control room on the ground. And the whole thing now becomes a lot more complicated in terms of managing your latency and doing real-time production. So we'll touch on these various things. Tomer, what do you think about latency? From your point of view, and our point of view is fairly narrow, what are the key contributors to latency in production systems, and where do you feel it's most important?
The key contributors in the devices in the production chain, or the bottlenecks of each product itself? You know, because
yes, go ahead.
Yeah, I'll start from the end. You know, you need the latency in order to do frame sync and those kind of things. So each device in the chain which needs to do any kind of processing needs to create its own buffer. So if you change those devices one after the other, then you have a bigger latency. So this is where the latency is coming from. Of course, for example, if you have a redundancy device taking two feeds and creating a single redundant feed, you need some latency in order to resync the two feeds, or whether we have the decision of whether he has a failure or not and do the switchover. You can't do a switchover before there is a failure, so you always need some gap, some delay buffer in order to get to this decision. Any processing of the video requires some lines to be in the buffer in order to create any kind of filtering or whatever, scaling, even logo insertion. So each device on the chain needs some kind of a latency just for the algorithm that it implements. And when we're adding the IP into the equation, then we have also IP buffering and the 2110 standard, which defines the synchronization of the frames and frame alignment and so on. So which again introduces additional latency parts to the chain.
So in a multiviewer, we have, a minimum requirement to put a picture together for the output. And so that dictates there's a minimum amount of latency required just in the multiviewing process. But can you talk to me a little bit about ways to measure latency?
Yeah, so the obvious, simple way is just to compare two sources, the reference source without one block, one processing unit in the middle, and the result after this processing unit. So the difference between the two will give you the additional latencies that this unit added. But again, even to do this kind of a measurement, it's very depends how you measure it correctly. Because if, for example, all of the devices are doing frame sync and the device in the middle is adding latency which is not a full frame, then the device afterwards will do the frame sync and will add some additional latency. So the latencies that you'll measure will be the total latency of multiple devices and not just of the additional device. So it depends how you measure it. And also it depends if you measure full frame latency or half or quarter frame latency or a portion of frame latency, because then it's a completely different game and then you can't work with a synchronized system. A synchronized system can only measure full frame latency.
Yeah, especially in 2110 where we're required to realign transmissions. Have you ever encountered people using a still camera to take photographs of the screen or a pair of screens, one with source, one with output? Have you experienced that, and any comments on how well that works?
Yeah, it starts from the setup itself. When we started going to the low latency numbers, we had to also measure it, not with a stopwatch, just with something which is frame accurate. And we started by measuring with a camera. And even in order to measure with the camera, you need to set up the field in order to do so. So you need to make sure that the screens are the same model of screen. You need to make sure that all of the devices are configured to the same settings and so on. And then when you're taking the picture in order to measure the difference between a frame counter, it also means that you need a frame counter to be inserted into the frame. It's easier with a number running. But then we found out that if you do the basic thing, which is taking a shot with your mobile phone, sometimes you see multiple numbers on the same frame, or see numbers going backwards and so on. And our understanding is that the cellular phone, for example, is doing some kind of interpolation on multiple frames and so on. So the best way to do it will be to take an SLR camera where you have a physical shutter. Even with the camera with the physical shutter, again, you need to take into consideration that you have some screens which are doing processing. So again, you need to use a professional screen or a computer monitor where there's no processing done to the video. Otherwise, you can't really count on what you measure. And even so, usually the best way to do it after you do it a few times to replace the two devices, meaning that to connect the other screen around and so on, and just to do a sanity check so the result is persistent and the equipment is not creating any different latency, which is not a result of what you're measuring.
So is there any relevance to measuring a latency that is in an increment less than a frame? I mean, is there any validity actually measuring, for example, the RTP timestamp on the source and the RTP timestamp on the mosaic output? How useful is that to a system builder to do that kind of precise measurement? Or is this really something that really is only meaningful in units of a frame?
No, it is meaningful. Of course, if you have multiple devices which are adding latency, if you can go to a lower latencies in a frames, then it's very important to know where you are. The RTP timestamp is relevant only if you're measuring latency which is added by IP devices, which doesn't restamp the timestamp. For a multiviewer, for example, which creates a new stream, which is not the same video as the source stream, looking at the stream itself is useless because you might have the same RTP timestamp, but the content itself, the video content, will be completely different. So for a multiviewer specifically, it's more complicated. If it's just a device that is doing some kind of processing and the video stays the same, then a visual comparison can help. Again, the RTP itself, the RTP timestamp is something that you can't trust ever because it has to be restamped by any devices, which is not just a switch. So you need to look on the content. Now, measuring values which are below a frame, first of all, if you are in a production chains, and yes, in the end, you need your content to be frame aligned. So it is full frames latency. But if the end result is a display for a multiviewer, for example, then you don't care about frame alignment because this is the end client of the content. And in this case, if you have a converter which will convert the 2110 feed back to HDMI based on the lowest latency possible and not doing frame alignment, then you can win maybe half a frame, maybe more, depends on on what you can create. And if the lower the better, why not? So in this case, yes, lower than single frame latency or not integer quantities that do make sense.
Yeah, and I guess it's interesting to note that 2110 strictly doesn't allow you to transmit except on a frame aligned boundary, but of course you can do that without impact if you're just going to a single piece of terminal equipment like a display. So that's interesting. Talk to me about Interlace for a minute. Both Interlace sources and their processing and how latency is affected there, and also using Interlace from the multiviewer to the display. Is there any advantage? I mean, there was a time, obviously, Interlace existed to try and deliver better motion behavior from 30 frames or 25 frames per second. In today's modern world, is there any benefit going interlaced from the multiviewer to the display, but also handling of interlaced sources?
Yeah, so it's a complicated question with lots of parts. So I'll go back to the compressed content. When you're handling compressed content, the two fields are combined into a single frame. And they are sent as a single frame and being decoded as a single frame. So your decoder gets both fields at the same time. There's no time gap between the fields. Now, when you're talking about uncompressed, then the two fields are transmitted one after the other. So you do receive the first field earlier, half a frame earlier than the second field. So on uncompressed, you can use the interlacing in order to shorten the latency in some way. You can create faster motion. But also you can just go to higher frame rates. You can move from 30 to 60 frames per second and have the same lower latency and higher quality of video without doing lots of interpolation. Because when you're using interlaced and you're going to need to go back to progressive for the display, you have to do it interpolation. And this is the second part of your question. I think all of the screens today are progressive screens with progressive scan, usually LCD screens, and those get the whole frame as a single unit. So interlace is not a native format for them. You always have to do deinterlacing, and one of the fields has to wait half a frame time. So there's no real benefit. When the screen is a CRT screen, then yes, it's native interlaced, and there's no additional latency, and there is an advantage using interlaced. But I think I didn't see a CRT screen for years now. It's not existing anymore.
Yeah, thank goodness for that. So let me ask you one other question. No, actually, let me not. Let me move on to something. So, we have all these pieces, and maybe we could try and quantify a little bit some of these delays. But also just understand where they fit in the chain. And, the first source of delay, I think we have to remember, and this is an adjustable delay because this is recalibratable because we're human beings, and that's the human factor. That's where the director yells, take, and the vision mixer, the technical producer has to get his finger down on a button, and the big high travel switch goes down, and the tally light comes on the control panel. But the video hasn't switched yet. There's a whole bunch of things involved there. So there's, first of all, that human formula, and we can't do anything about that. But from the time that button goes down, a number of things have to happen. The vision mixer has to change source or commence the effect or do whatever. And although that's not really a significant delay, very often it's triggering, for example, the beginning of a fast dissolve. A small number of frame dissolve. So the actual latency from button push to that dissolve beginning is a little hard to tell until you get a couple of frames into that dissolve. On a take, of course, you see that right away. Within the vision mixer, we have a whole bunch of processing to do. The vision mixer does a lot of compositing. It's doing this in frame buffers. And typically, vision mixers, although they're designed for minimum input-output delay, incur delays in other ways, such as when you route signals through a DVE. Maybe you're on a full-screen DVE waiting to do a squeeze back, in which case you're looking at a signal that's already a frame delayed because it's living in the DVE's frame buffer, or perhaps more, depending on the DVE. At that point, when it escapes the switcher and makes it across whatever protocol, we get it into the multiviewer. The multiviewer has to aggregate all of these pictures, which are, of course, synchronous, so they're all arriving at the same time, and it has to put them together and turn them around into a single outgoing feed for display. And that's all fine. Then we have the display converter, and here's where we get into a bit of a potential variability because of choices vendors have made. And in my own experience, for example, when we go from 2110 to HDMI, the typical scenario for driving a display, we may find different delays in display converter devices of different vendors. You may find a frame sync in this display converter, and that frame sync may in fact be arbitrarily adding some amount of delay to your picture processing. And then, only then does it make it on the HDMI into your display. Once you get into your display, you're into the Wild West, because everybody who has a TV set knows that there's a million controls to adjust all sorts of things, such as noise reduction, motion compensation, high frame rate interpolation, and things like that. And these all take frame buffering inside the display device. And very often we discover that people are running a control room and seeing some high latency. You go to the menu on the TV display and you discover they've got various features turned on, which incur additional display latency as well. So going back to where I sort of started the story, with the little electron beam scanning a camera tube and somehow that within tens of microseconds landing on the beam of a viewer's set, we now have huge amounts of time between the light in the studio and the light in the viewer's home. So these are all factors that get it at least into the control room on the display. But let's talk about live a little bit further, and that's going downstream. So if we're going through traditional distribution channels, we might be getting encoded for pay TV, we might be getting encoded for regular transport stream distribution, we might be getting encoded for OTT. And if we want to talk about latency contributors, there's a place to talk about latency. I don't know, Tomer, do you have any comments about the latency in distribution versus the latency in production?
Yeah, in production you measure it by frames. I think that in distribution you measure it by seconds. It's completely different numbers, and it has also a different effect. In the end, the customer at home doesn't need to push the editing button, so he doesn't care if he sees it 10 seconds later. There's no effect unless he's on a live interview on the TV, and then he shouldn't look at the screen.
Yeah. That's right. Turn down your radio when you're on the radio interview, I think is the old joke about that. Yeah, very true. And, you know, that feeds back a little bit into what is the meaning of overall latency. And what it comes down to is in a control room, you need sufficient latency, sufficiently low latency to be able to produce your show without artistic limitations. But once it leaves your studio, it's not like the old days where it went directly to a transmitter on a hill and was transmitted. It now can go through a number of distribution channels, every one of which includes some contribution of latency. And it gets worse, right? Let's go one step further, because the hot topic today, thanks to COVID and just people looking for modern workflows, COVID has of course accelerated this, is working from home and remote production. Because that implies then that we're at least doing contribution through the cloud or through the internet. When I say internet, of course, you can substitute the word latency. If we're doing a production system in the cloud, we have latency issues related to controlling that from a ground-based control room, because we need to get signals down from that in a timely manner. And so the link down from the cloud, in fact, probably becomes one of the biggest control room latency issues going in a system like that. And we have some tools available. Tomer, talk to us a little bit about the sort of tools we have available to get to and from the cloud in a safe, secure, and low latency manner nowadays.
Well, there's lots of protocols in order to encapsulate content and push it to the cloud. It's based on, unlike a regular delivery, which is TCP. TCP is a delivery of IP protocol where you have acknowledge protocol, and it creates an non-constant delay because the protocol waits for receive acknowledge. And the other method is UDP, where you send the datagram, the packet, the information, and you hope it will get there. With this method, you can go to lower latency, but the problem with this method is that if some of the data doesn't arrive, you have a problem on the video. So for this, there's lots of protocols like the ZXC, the SRT, the RSAT, which are doing a combination of things, which in a large envelope, we can say that it's a forward error correction and managing the bandwidth of knowing what to send multiple times or more, and how to send, how to choose the route. And the bottom line of those protocols is the ability to send streams to the cloud in considerably low latency. And we were saying considerably low latency, we're talking about seconds. Previously, without those formats, you have formats which are file transfer, which is, file transfer is really slow, but let's take the standard OTT like HLS, MPEG-Dash, and Microsoft Smooth Streaming. All of those formats are, in the end, file transfer protocols. The content is cut into small chunks. Those chunks are being sent as files, being converted back to a stream on the other side, and so on. And in this case, the latency is a factor of the chunks, and we're already talking about high numbers of multiple seconds of latency. So all of the new protocols for transferring data to the cloud are based on streaming, meaning that the latency is much, much lower. But still, we're talking about area of seconds. Let's say that if you have a dedicated fiber, you can go to below a second. But still, again, depends on the bandwidth, on other parameters, distance from the part of the cloud that you're going to use and where you are. This is also something that people sometimes don't take into consideration. When you're using the cloud, it depends where is this cloud located. So it's not just uploading stuff to the cloud.
Talking to you on this reminds me of something relevant, and that is the old remote satellite news stand-up, where the reporter goes to the site of the disaster and they set up the satellite truck, and then they do a live interview. And just like you and me, I don't know what our latency here is, but with 250 milliseconds up and down to the satellite, it makes for a jerky interview with a bit of dead air with every question. So interestingly, I've observed and had people say to me that it's actually worse today in live remote production than it is with satellite links for remote stand-ups, simply because of all the cumulative delays in the cloud-based production system. So it's kind of funny to see us move to technologies that end-to-end kind of move us backwards in the short term. I've also seen productions done and been in the control room watching the change in behavior because the visual confirmation comes late when you're doing live remote. So in the control room, they're making decisions often on ISO feeds they have incoming through a separate route, just so they can see them quicker than they can see them through the production system in the cloud. And then they're making switch decisions into that production system and then looking at the result when it finally gets back down to the ground sometime later. So it's interesting to see people adapt to these workflows. And I initially thought that it would be really miserable and people would fall over, but it actually seems to work out pretty well. Seems human beings are quite adaptive at this sort of thing. But it definitely has changed the game in production. And it's also changed people's awareness about latency and also perhaps reduced people's concerns about latency in production systems a little bit, only because the control room and its systems are now the least of the problem when it comes to end-to-end latency in production systems. We have some questions, and we have some good questions. So if you're okay, Tomer, maybe we could pick up a few of these questions and see if we can answer them.
Yeah, only the good questions.
Oh, okay. Number one looks good. It's assumed that all 2110 production switchers have a full frame sync on each input channel to line everything back up to account for variable processing latency on each channel. That's a good question. We don't have a lot of input on true native 2110 production switchers yet. They are emerging. A lot of the 2110 production switchers today are gateways in front of essentially SDI or 2022.6 backends. I assume people will put frame syncs on every input for a number of reasons. One is to do a clean freeze, for example, on loss of input, also to get them the timing flexibility. But at the same time, if you're going to implement a frame sync on the front end of the production switcher, you're going to implement some delay by design. So a frame sync is a good thing, but operating it in a minimum delay mode, where it's, for example, accommodating, say, the wide buffer requirement of a wide transmitter and no more, would be a good thing. Now, there's always been auto timing buffers on vision mixer inputs. A frame is convenient because then you can run a non-synchronous source. But if you're running a serious low latency production, you want to run that input buffer in a fairly tight way and have all your sources within a line or two of video timing into the switcher. So I guess it remains to be seen what people will do with vision mixers. The frame sync on the input is good, but managing that latency, I think, is very important. Question 2. It'll be interesting to learn about Tomer or Paul's or TAG's real-world experiences examples caused by variable delays such as jitter, and how it typically impacts a typical TAG customer. Well, we could talk about delays, I guess. I mean, I have my own little speech on this, and that has to do with wide transmit profile in 2110, resulting in the need for 2 different receive buffer models, but the narrow receiver becomes useless because if you have a wide transmitter in the mix, then a narrow buffer can never be used. Of course, we're not constrained to hardware, so our jitter experiences are possibly not as exciting as some other people's. Tomer, do you have any comments on experiences we've had related to variable delays? And jitter is in brackets here, but I guess we're talking wander and jitter together on streams.
No, it's 2 different things because having the frame not aligned, you need a buffer in order to realign it. But jitter, it also means that you have non-constant latency or burst of information. And this is a more dramatic problem, especially on a multiviewer, because if it's just a converter converting from 2110 to HDMI or so, or vice versa, then the load on the fiber is quite low. It's a single channel. It's not really an issue if you have some burst. But with a multiviewer, you try to push lots of sources or channels into the same multiviewer on the same fiber. So if you do have some sources which don't behave and have some burst of information, then it can't really fit in the fiber, as long as you're trying really to load the fiber. So you have to take into consideration these factors, that if your sources are not narrow sources and not completely stable, you can't really use the fiber to its limit. And we've been talking about using a fiber to its limit. For example, a 100 gig fiber is just about for 30 channels of 3G, maybe a bit more if you're taking into consideration the 2110, which is not taking the full 3G bandwidth, but you have some audio feeds and so on. So in the end, it's something between 30 to 40 channels, depends on the frame rate. So, and this is a normal number for a multiviewer. And if some of those sources have bursts of information, you'll have to keep some spare for those, so you can't really get to those numbers. So this is why jitter is a problem, is an issue, not just because of the buffering. And if we're talking about frame alignment, then again, it's as you described regarding the vision switcher. If you have a frame buffer, it means that you need to add delay. If you don't want to add delay, you can't handle frames which are not aligned. In software, it's easier than doing it in hardware because you can change the behavior dynamically. So if the source is synced, you can work without a frame buffer, and if it's not synced, you can you can add a frame buffer dynamically, so it's easier. But still, you can't expect to have the same behavior with those 2 types of sources. And of course, this is before you add into the equation the ability to combine different frame rates, interlace sources, progressive sources, and so on, where you definitely need a frame buffer and the ability to handle non-aligned sources, because a 25 frame per second source can never be aligned to a 29 frame per second.
So just a question here about AV sync. And the question was, any comment on using fingerprinting that some manufacturers insert into the metadata at the sources to measure delay through a signal path? And I'll give two quick answers to this. Yes, I have comments. Fingerprinting to measure AV delay is a very, very good technique. It counts on you being able to measure the AV delay at a point where it's known to be good, and then establishing a fingerprint or a signature of some kind that conveys that unique information downstream in metadata, so that downstream you can perform that same analysis on the content and then try to match the fingerprint and find the frame nearby, hopefully the same one, hopefully not an earlier one, but usually a later one that matches that fingerprint. There's two ways this can work. One is to insert that fingerprint into metadata, and actually there's a SMPTE standard, ST2064, describes generating these fingerprints and inserting them into metadata. There's also a technique where we can insert that metadata into a watermark in the video or audio. And I raise that as a second point only because that works really well until you start processing the video and audio. And at that point, the watermark can be damaged, lost, become noisy, a signal to noise problem with the watermark, and so on. So typically the fingerprinting method is the most robust. And I'm happy to hear that some manufacturers are doing this now. I don't know if they're using the SMPTE 264, but that standard does provide very, very reasonable ongoing non-reference based audio-video synchronization measurement, in that it doesn't require the reference, it just requires the fingerprint from upstream. The beauty, by the way, of that technique, not doing a selling job here, but we can actually use that right down to the set-top box. So someday, somebody may elect to put this into a place so that we can actually fix the fingerprinting right before it goes into the TV set. And the TV set probably breaks the lip sync going down the HDMI coming into the set, but that's yet another story. Number 4. We have used a light-dependent transistor into a 2-channel scope to measure a screen which has a black-to-white transition. I get this. That's really cool. What do you think of this approach? I mean, 2 screens and 2 transistors into the storage scope. I think that's great. If you have a screen that goes from white to black on a frame transition and you can trigger the scope and then watch for the following screen to do the same thing, you can measure it in precise units of time. So that's a really, really good way to do it. The other way I've used, by the way, Tomer mentioned using an SLR. I've also used a 60 frame per second video camera, which also works really well for this purpose, because at least on a 60 frame basis, you can see what's happening. But doing what you're doing, you can actually get some measurements in actual units of time. So that's really quite cool. Number 5, I think I just might have answered that. Latency can be measured with a video recording, but in that case, we have to count the FPS of the recordings, the measurements through the video sampling. Though the video sampling time by frame rate of the video, right? Yeah, you're going to be limited. So if we have 30 frame video and you're shooting with a 60 frame camcorder, you're getting 2 frames of camera time for each displayed frame. The challenge there is that shutter open time for capturing one of those 60 frame per second frames could span the display change. So the SLR is a good method, but actually the phototransistor and blinking light method is probably your best way to get an absolute time measurement. Yeah. Number 6, I see multiviewer latency as 2 frames. Is that a limitation created by implementing in a CPU with a non-real-time OS? I will answer and say no. I will say partly that's standards-based, and I'll throw to Tomer for more detail on that.
Okay, so first of all, we'll start from the physics. You can't go below a single frame latency on a multiviewer, and the reason for that is very simple, that if you have a frame which you scale to a very small tile in the top of the video, then you need to transmit the last line of this frame at a very high point. So you need to, in order to be less than a single frame latency, you need to go back in time. So since this is not possible, then the best multiviewer ever can only have a single frame latency. So this is with 0 additional latency. Now, the problem when you're talking about IP multiviewers or any IP devices is that you need to create a very paced transmission of the packets based on the 2110 timing model. And in order to create this timing model, you need to have some kind of buffers on the transmitting hardware, because the software can't create the packet on the CPU and send it on the fiber right away. It goes from the CPU to the memory, to the PCI bus, to the network card, and being sent on the fiber. So you have some kind of a delay in the middle, and you also have some kind of a jitter on this delay. And in order to remove the jitter, you need to create a buffer on the side near the fiber, as far away from the CPU and close as possible to the fiber itself. And this delay is, this buffer is latency, is a delay. And the same you also have on the receiving side. You need to receive multiple sources, and you need to handle all of those sources. And usually you don't want to handle a single packet each time. You want to handle bursts of packets. So you collect those packets on the receiving buffer and handle either full lines or stripes of content. So this is also adding additional latency. There is a way to manage everything in a lower latency, which is to create everything not on frame boundaries, but on portions of frame slices. Then you can go to lower latency. So 2 frames latency is not the limitation. We also support lower latencies than 2 frames. Based on those methods. Of course, supporting 2 frames is the easiest way. You have a full frame buffer on the input, and you can create the output and send it out. So it's quite simple. The issue is that removing the latency means that you remove buffers. Removing buffers means that you're more sensitive to bursts of inputs coming in or processing need. So it means that you can load the system less, you can use it less. So there is some kind of balance between the amount of what you want to do and the latency, because in the end, a multiviewer needs to support large number of channels. A multiviewer of 2 channels is not really a multiviewer. So if you want to support 40 or 80 sources, then you need some kind of a latency in order to synchronize everything all together.
And of course, when you go to the cloud, all of that falls completely out of bed because it's a different equation anyway. But in a tight production system, your point about leaving headroom for the network to ensure the network is stable and reliable is an important thing. And again, yet another contributor to latency. We have a couple more questions here, but in the interest of time, I think what we'll do is wrap it up now. We will be answering all of the questions submitted and sending them out to everybody by email. So you can watch for that. I'm sorry if we didn't get to your question. And we will do that shortly. And of course, we're happy to talk to you about your multiviewer needs or any of your technical issues related to 2110 or production control rooms or control room systems. Also like to invite you to play with the TAG product itself. We can offer a very quick stand-up demo where you can actually sit down and configure and operate one of the TAG Multiviewer products and play with it. And it's a great opportunity to see what multiviewing in the pure IP domain is like. And so with that, I would like to say thank you. Thank you, Tomer, for your time. Have a wonderful afternoon and evening in Tel Aviv.
Thank you. It's always a pleasure to have those webinars with you.
Thank you, everyone, for attending. We appreciate your time. We know it's valuable. And we hope you've learned something useful here today. And if we can help you out in the future, or you'd like to give our stuff a try, please, by all means, contact us through one of the many means available to you on the links to the webinar and so on. And with that, thank you.